NENOMATICA, where mathematics meets YouTube excellence. We will process a problem about radical inequalities and reproduce the exact step-by-step solution in English. First, here is the example, and the inequality we will solve. Now, we follow the structure shown in the source. Step 1 defines the domain of the radicals. Both radicands must be non-negative. We write the two inequalities and then intersect them. Next, we isolate one radical and square both sides exactly as the written solution does. Start from the given inequality, add the second radical to the right. Now square both sides. We expand the square on the right using the binomial formula, then simplify by combining like terms. First expand. Now simplify and cancel the x terms on both sides. Finally, isolate the radical term. Divide by 4 and square again, 4 and square again, to remove the remaining radical, keeping the inequality direction since we divide by a positive number. First divide both sides by 4, then square both sides. Now solve the linear inequality for x. Add 4 to both sides. This yields the bound on x. Finally, intersect this with the domain x greater than or equal to 4 from step 1. The intersection interval is the solution set. As a quick challenge, test a value inside and outside the interval. Quick challenge. Pick x equal to 5, then evaluate the left side. It should be greater than. We will solve a radical inequality step by step, following a clean algorithm and checking domain restrictions carefully. Here is the example we will solve. Step 1. We simplify the structure by introducing a substitution. Let y equal the square root of x squared plus 5x plus 28. This turns the inside of the radical into a single symbol. From the definition, y squared equals x squared plus 5x plus 28. Subtract 24 from both sides to match the left expression. Y squared minus 24 equals x squared plus 5x plus 4. Step 2. Substitute into the original inequality. Replace x squared plus 5x plus 4 by y squared minus 24, and replace the radical by y. We get y squared minus 24 is less than 5y. Step 3. Move all terms to the left side. This gives a standard quadratic inequality in y. Y squared minus 5y minus 24 is less than 0. Step 4. Factor the quadratic. Y squared minus 5, y minus 24 factors as left parenthesis, y minus 8 right parenthesis times left parenthesis, y plus 3 right parenthesis, less than 0. Step 5. Use a sign chart for a product to be negative. The product is negative between the roots, so negative 3 is less than y, which is less than 8. Step 6. Account for the domain of the square root. Because y equals the square root expression, it must be non-negative. Therefore, y is at least 0. Combining with the previous interval, we get 0 less than or equal to y, and y is less than 8. Step 7. Substitute back for y. That gives 0 less than or equal to the square root of x squared plus 5x plus 28, which is less than 8. Step 8. Since the square root is non-negative, we can square the right-hand inequality safely. This yields x squared plus 5x plus 28 is less than 64. Step 9. Bring all terms to one side. We obtain x squared plus 5x minus 36 is less than 0. Step 10. Factor the quadratic in x. It factors into left parenthesis x plus 9 right parenthesis times left parenthesis x minus 4 right parenthesis, less than 0. Step 11. A product is negative between its real roots. Therefore, x lies strictly between negative 9 and 4. We will also visualize this on a number line. Welcome! In this example, we will solve the inequality involving an absolute value and a square root, following a clear step-by-step structure with rule boxes before each transformation. Right below the label, we will display the problem in bold orange math. Step 1. Determine the domain of the square root. The radicand must be non-negative. This yields x plus 1 greater than or equal to 0. So x is greater than or equal to negative 1. We denote this domain as d1 equals open parenthesis negative 1 plus infinity close parenthesis. Step 2. Square both sides because both expressions are non-negative. we have absolute value of x minus 1 less than or equal to square root of x plus 1, which after squaring becomes quantity absolute value of x minus 1 squared less than or equal to quantity square root of x plus 1 squared. That simplifies to left side x minus 1 quantity squared and right side x plus 1. Step 3. Expand and simplify. Expanding x minus 1 quantity squared gives x squared minus 2x plus 1. So we have x squared minus 2x plus 1 less than or equal to x plus 1. Subtract x plus 1 from both sides to gather to the left. We obtain x squared minus 3x less than or equal to 0. Step 4. Factor the quadratic expression. We factor x squared minus 3x as x multiplied by x minus 3 and keep the inequality less than or equal to 0. Step 5. Solve the inequality by sign analysis. The roots are x equals 0 and x equals 3. The product x times x minus 3 is non-positive between the roots, inclusive, therefore the solution set is D2 equals the closed interval from 0 to 3. Let's visualize this on a number line. Step 6. Intersect the domain from step 1 with this solution set. D equals D1 intersect D2, which equals open parenthesis negative 1, plus infinity close parenthesis intersect with the closed interval 0 to 3, giving the final answer 0 to 3 inclusive. Step 1. Determine the domain. The expression under the square root must be non-negative. And because the right side is x, for the inequality with the square root to make sense when we square later, we also need x greater than 0. Now factor the quadratic and state the domain set. Step 2. Square both sides. Because from the domain we have x strictly positive, squaring preserves the inequality direction. Write the inequality and then square both sides. Step 3. Simplify by subtracting x squared from both sides. Step 4. Solve the linear inequality. Add 4x to both sides and then divide by 4. Step 5. Combine with the domain we found earlier. Intersect x greater than 3/4 with d equals open 0 to 1 bracket union bracket 3 to infinity. Let us visualize the answer on a number line for intuition. X greater than 3/4 with d equals open 0 to 1 bracket union bracket 3 to infinity. Let us visualize the answer on a number line for intuition. Therefore, the complete solution set is open parenthesis 3/4 comma 1 closed bracket union bracket 3 comma infinity. Great work following the exact algorithm. Summary. We found the domain, squared the Here is the problem statement. Step 1. Calculate the domain of the expression under the square root. We use the rule that a square root is defined only when its inside is greater than or equal to 0. Now we write and factor the inequality to find the domain of the radicand. Next, we factor the quadratic. From the sign chart of the factors, we obtain the domain for the radical. Step 2. Analyze the product and determine a working domain to guarantee a non-negative product when the radical is strictly positive. Because the square root is always non-negative, the sign of the product equals the sign of x minus 1 whenever the square root is positive. We therefore impose x minus 1 greater than or equal to 0 to steer the sign non-negative. This gives the helper domain D2. Step 3. Intersect the domains. The overall working domain is the intersection of D1 and D2. Step 4. Check any boundary where the radical equals 0. If the radical is 0, the product is 0 regardless of the factor x minus 1. We test x equals -1 in the original inequality. It evaluates to 0, which satisfies the inequality. Step 5. Write the final solution set. We combine the intersection with the additional solution at -1. Quick challenge. Why is x equals 1 not included in the... Welcome! In this example, we solve a radical inequality step by step and visualize each set on a number line. First, here is the example and the original inequality. Step 1. Compute the domain of definition. The radicand must be non-negative, and denominators cannot be 0. We set 6 plus x minus x squared greater than or equal to 0, factor the quadratic, and then state the closed interval for which it holds. We also exclude the points that make the denominators 0. Step 2. On the open interval from -2 to 3, the radicand is strictly positive, and both denominators are positive as well. This lets us safely divide by the square root and compare reciprocals without flipping the inequality sign. Step 3. Because the square root factor is positive on this interval, we can cancel it from both sides. The inequality becomes 1 over 2x plus 5 is greater than or equal to 1 over x plus 4. Step 4. When both are equal to 1 over x plus 4. Step 4. When both denominators are positive, comparing reciprocals reverses to comparing the denominators directly. 1 over is greater than or equal to 1 over b implies a is less than or equal to b. We obtain x less than or equal to -1. Step 5. Intersect the solution with the domain. The intersection of the closed interval -2 to 3 with a set of all x less than or equal to -1 is the closed interval from -2 to -1. Quick challenge. Pick a value inside the final interval, such as -1.5, and verify it satisfies the original inequality. Then try a value outside, such as 0, and see it fails. Great work! Summary. We computed the domain from the radicand and denominators, used sign analysis to safely cancel the common square root, compared reciprocals to obtain x less than or equal to -1, and intersected with the domain to get the final solution set. To obtain x less than or equal to -1, and intersected with the domain to get the final solution set. Practice more problems like this to build fluency. Example. Solve the inequality square root of left parenthesis x minus 3 right parenthesis times left parenthesis 2 minus x right parenthesis is less than square root of 4x squared plus 12x plus 11. We will follow a precise step-by-step algorithm. Step 1. Calculate the domain of the inequality. We use the rule. A square root is defined only when its radicand is greater than or equal to 0. So both radicands must be non-negative. The first product gives the interval 2 to 3, closed. The second quadratic has negative discriminant and positive leading coefficient, so it is positive for all real x. Step 2. Solve the inequality inside the domain. Since both sides are non-negative on the domain, we can square both sides. Square root a less than square root b implies a less than b. Expand and simplify the left product, and move all terms to one side. Multiply by -1 to make the leading coefficient positive, which reverses the inequality. Step 3. Analyze the quadratic inequality. A quadratic with positive leading coefficient and negative discriminant is always positive. Compute the discriminant of 5x squared plus 7x plus 17, 49 minus 340 equals -291, which is less than 0. Therefore, the inequality holds for every real x. Step 4. Write the solution set. Because the inequality holds for all real numbers, the only restriction comes from the domain, which is the closed interval from 2 to 3. Thus, the solution set equals bracket 2, 3 bracket. Step 1. Calculate the domain of the inequality. We apply the rule about domains of square roots. The inside must be non-negative. Step 2. Square both sides of the inequality, but only within the domain, where both sides are non-negative. We expand and carefully rearrange to isolate the radical product. Step 3. Analyze the sign of the right-hand side, -16 minus 7x, on the domain from 0 to 5. Evaluate at the endpoints to conclude its sign across the interval. Step 4. Step 4. The left-hand side, 2 times the product of square roots, is always non-negative on the domain. Step 5. Since the left side is non-negative while the right side is strictly negative over the domain, the inequality strictly holds for every x in the domain. Welcome! In this example, we will solve a radical inequality step by step, mirroring a structured workbook solution. First, let's display the example and the problem. Step 1. Determine the domain of every square root. The square root of f of x is defined when f of x is greater than or equal to 0. We factor each radicand and write the corresponding intervals. Intersecting these gives the working domain for the inequality. Domain intersection. The intersection is -∞ to -5, closed, union 5 to infinity. Step 2. Square both sides. Because all 3 radicals are non-negative on the domain, squaring preserves the inequality direction. A greater than b implies a squared greater than b squared. If a and b are non-negative, we square both sides and expand the left using the binomial pattern. Now we combine like terms and move them to the right to isolate the mixed radical term. The sum on the left is 2x squared minus 6x. Subtracting from the right yields 2 times x squared minus 6x plus 9, which is 2 times x minus 3 squared. Divide both sides by 2. We obtain the key inequality. The product of radicals is greater than x minus 3 squared. Next, combine the radicals into one square root, and then square again. The square root of a times the square root of b equals the square root of ab. Also, each quadratic factors neatly to show a common x minus 3 squared factor. Since both sides are non-negative on the domain, we can square again. Divide both sides by x minus 3 squared. This is safe because on our domain, x equals 3 is excluded, and the square is non-negative, so the inequality direction is preserved. After division, we compare x squared minus 25 with x minus 3 squared. Expand the right side and solve the linear inequality. Finally, intersect with the working domain. Since 17 over 3 is about 5.67, and the domain includes 5 to infinity, the intersection is open interval from 17/3 to infinity. Final solution set equals D1 intersect this inequality solution. Let's visualize it on a number line. Example, we will solve a radical inequality step by step, mirroring the structure shown. Here is the inequality written in bold orange latex. Step 1. Calculate the domain of the inequality so all square roots are defined. The rule states the square root of f of x is defined when f of x is greater than or equal to 0. We apply that to every radicand. Intersecting all 4 conditions gives the working domain. Step 2. Rearrange the inequality to compare differences of radicals. From a plus b less than c plus d, we may compare c minus a with b minus d. Here is the rearranged form we will analyze. Step 3. Split the domain based on simple comparisons of the radicands. We compare 5x minus 4 with 2x minus 1 and 3x minus 2 with 4x minus 3. This yields x greater than or equal to 1 and x less than or equal to 1, so we analyze 2 cases. Step 4. Analyze case 1 from 4/5 to 1. We check signs of each difference. The left difference is non-positive. The right difference is non-negative. Therefore, the strict inequality cannot hold here, so there is no solution in this interval. Step 5. Analyze case 2, x greater than or equal to 1. Again, we check both differences. The left difference is positive. The right difference is negative. Hence, the rearranged inequality is satisfied for x strictly greater than 1. Step 6. Write the final solution set. We summarize the valid part of the domain. Here is the solution in green. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.